Not only for his scholarship, but also for his sense of humor, which I don't know will be on display, but often is. Kevin, to the best of my knowledge, has the highest H-index of anyone in computational linguistics, significantly higher than mine. What can I say? And the really tough part to accept is he deserves it. So, without any further ado.
Okay. So after seeing the content of this talk, you may question whether I deserve it, and certainly you may not find it funny, but what can I do? Okay, so I'd like to thank Eugene, the organizers, for inviting me, and thanks to everybody for coming. So I'm going to talk about language translation and code breaking. If you have any questions, just to interrupt me during the talk. It's better that we do it that way, but I'll leave some questions time at the end too. Okay, I have like an hour, right?
Yes.
End around 5. Okay. So mostly what I work on for the last 10 years with a group at ISI at USC has been machine translation. So we take stuff like this that you may not be able to read, and we put it through software, and we output stuff that you can read. So it's Chinese to English and Hausa to English. And we try to do this as accurately as possible. This field goes back a long way to the 1940s when this guy, Warren Weaver, an information theorist, came up with a basic idea. He said, when I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode. And he got this idea from working in World War II, code breaking, and the guy sitting next to him was decoding intercepts from a code that they pulled down into Turkish. The guy didn't know Turkish. He could still do it because he knew how the letter frequencies and letter pairs of Turkish worked, and that turned out to be enough knowledge of Turkish to be able to decipher messages into Turkish. So you can see Weaver's got this idea, maybe a computer could translate into English without knowing English, because computers don't know English. Okay, and it was a mere 50 years later before his idea became something that was practical. So the idea here is there's a person or many people translating at the United Nations producing, let's say, Spanish translations of English documents. Huge millions and millions of sentences. We feed those to a learning machine. Learning machine says, every time this person sees banco, he types either bank or bench. But every time he sees banco day, he always types bank. He never types bench. And so this computer thinks actually for a couple of weeks, sometimes, crunches all that, and is then able to use what it learned to translate new text. So let's put ourselves into this task and see how a computer might do it. So what I've done is I created a smaller, not millions of sentence pairs, but only 12 sentence pairs, English and Spanish ones. Before you look at this, I want to put you in the mind of the computer. Okay. So what I do is I replace every English word "the" with some extraterrestrial Centauri word, and same thing on the other side. So now when a computer looks at the parallel text, this is what it sees. And what we want to do is be able to tell a computer, learn enough from this to be able to translate a new Centauri sentence, this one up here, into Arcturian language. Okay, so before we get to any computer algorithm, let's just try to do it ourselves. So this first word up here is Farouk. We can find it twice in the corpus. And can you guess what the translation is of Farouk into Arcturian?
Yes, but we don't know how to pronounce it.
You can spell it if you want to. They use Roman alphabet, so that's good. All right. So the translation is probably in 5b and 7b, and yeah, the only word that's common to 5a and 7b is jijat. That's how I say it. Okay, then we look at this next word, karak. No, it only appears once. So, and you can start to see that having a lot of data matters, right? If you only see something happening once, it's hard to draw a lot of conclusions. So let's just skip it. Go to hi-hawk. This occurs 3 times. We can guess what it means. Yorak only appears twice, but we can still guess. Here's another word, clock. It only appears once. But the strategy we're going to take here is, let's figure out what all these other words mean, and then we'll come back to it. And maybe, okay, here, and then maybe by pigeonhole principle, we could figure out its partner on the other side, and you can do that. So kind of a process of elimination. And humans use a lot of other strategies. So, for example, these 2 words, Zanzinak and Zanzanat, probably translations of each other, and so you can make progress here. And you can see we're building up a translation dictionary as we go, but also building up an alignment structure so that you can see there's a word order difference between these two languages. And you need to learn about that word order. So even if we can translate all those words up there, we need to put them in the right order and maybe insert function words. So it's not a trivial thing for us to do, but you can see how we'd approach it. Is that okay? Any question about that? I could use a question. It'll help me in the first 5 minutes. Yes?
You made a few, I'm trying to figure out what the assumptions are about good ideas to try, right? So there could be that there's 2-to-1 mappings and things like that.
Yeah.
That's something we skip.
Look at this word, Karak. I didn't even come back to that guy. He's left all alone, and there's no pigeonhole for him to go into. So it turns out that's the English word do, and do doesn't translate into Spanish. And so it's a complicated.
There's also, like, the banco example is interesting because the word bank originally comes from the word from bench.
Oh, really? Okay.
So, because they used to lay it out on benches in Florence.
Okay.
So in some sense, it's not a bad translation.
It's a bad translation. Okay, we can argue. Speaking of bad translations, so this field really got going academically as a discipline. It involved many researchers around the world. Only in 1999, at that time, it was possible to translate 1 page in a day. That's how long it took. So not fast. The quality was lower than you would get from the previous methods, which are kind of human, manual built rule bases. Limited domains, only French, English, and no commercial offerings. So now we've got fast systems, over 50 languages. You probably use translators on the web. They're free. The quality is much improved. It's better than the previous sort of technology. And if you want to buy products, if you're a business or intelligence, then you can buy products now. And just to show you an Arabic translation, and you can see what you think, Somali President Sharif Sheikh Ahmed during a visit to sites of government forces and African in the district of Howden in Mogadishu, that the current military campaign will not stop until Somalia is liberated from the youth and Al-Qaeda. Okay, so if you're a glass half full person, you're like, wow, 5 years ago, we couldn't translate this at all. And you had to hire an Arabic speaker, and they would, the glass half empty part is, hey, there's a bunch of stuff, it's not grammatical, and do you really want to liberate the country from the youth? And there's probably some strange things. So we still have a long way to go to make accurate translation. And in particular, Arabic is kind of middle. French is very good, but Korean and Japanese translation is super bad. Chinese somewhere in between Korean and Arabic. So many, and that's not even to mention thousands of languages, and they're spoken in Africa. How are you supposed to translate these into English and back and forth? So long way to go. Yeah.
So do you think that's because less work has been put into those languages, or is there something about the language?
There's a bunch of stuff, and it's a mystery, but not enough data to train on. That's a big thing, and in general, it's more like the further a language is from English, like say Japanese, they just say everything different. It's just, it's not a matter of because they put the verb at the end, this we could handle. But everything's different. If you just want to say, that person's pregnant, in English you just use the adjective pregnant. But in Japanese you'll just say it in a different way. And so every kind of mundane phrase is just said in a different way. And you have to memorize it, but you also have to memorize it, how it works in different contexts. That's the best answer I can give. So, but for sure, there's lots more work we have to do in all these things, and people are trying all different kinds of stuff. So I'll just mention one because it ties in with the rest of this talk that we work on at our place, and others are working on. This parallel data is kind of a bottleneck. So for many language pairs and domains, we don't have a lot of human translated material. So this is the usual way we do things. But here's an alternative to try to consider, which is certainly you can get a lot of plain Albanian text that's not translated. Much more. And much more English. And could you somehow decipher this Albanian into English and again build up a dictionary and be able to learn enough knowledge to translate new stuff? And I'll come back to this towards the end of the talk, and we can see if that's a crazy idea or something realistic, but that's an ongoing research topic. Okay, so to work our way up, we're going to start back with some simpler types of deciphering and way back in the Warren Weaver era. So this is a German army encryption machine that was used in World War II. It's a substitution system, so you type N, and it lights up J, and you send J across the radio to your buddy. The neat thing about this machine is when you're encoding things, the substitution table changes every time you hit a button. So some wheels turn inside the machine. So you hit N, it doesn't just say JJJ, it says JTE. So the substitution scheme changes. And then depending on how you initially set up the machine, so you set up the machine initially, everybody agrees on a setting for a certain day, so that everybody can talk to each other, by setting the wheels in a certain place. And the final neat thing about this machine is, if you type N and you send JTE across the radio, your buddy on the other end just types JTE and he gets N out. So it has this kind of reversible, very practical behavior to it. Okay, so if you're German, no problem. If you're, say, British, all you can do is intercept these radio transmissions. You don't have the key. So what you have to do is you guess key. And you apply it to the cipher. You set up a machine with that key, those initial settings, put in the cipher and see if what comes out is German. So how do you guess a key? Well, there's billions and billions of keys. What we would do today, statistical machine translation, we have just done it, right? You take a parallel text, translated text, and you build some aligner, and you learn how the relationships between the plain text and the encoded text. Okay, so that's how we would do it today, but that's we don't have this kind of ciphertext and plain text. You know, they didn't have that during the war. They just have the ciphertext. Yeah.
But even then, it's a different problem, right? Because first you have the seeding of the keys, and you also have the words keep changing depending on which.
Actually, last summer I worked on this alignment problem. So given an Enigma message, the plain text, and you try to recover the initial settings, it's not trivial. It's not as simple as what we did, but you can do it. But this is way, way harder, where you just have to guess the key. And it turned out the Polish scientists, even before the war, had kind of got onto this. And they wired up a bunch of Enigma machines together. And it's not really a computer, but at least it's an electromechanical decipher machine where it just starts exhaustively moving the wheels around, looking for a key that will generate a certain plain text pattern. And when it finds one, it stops. And then actually a human checks to see if the output is German. And if it's not, they turn the machine back on again, and it keeps searching. And the human says, okay, now this is German. You can imagine maybe we should write a computer program to tell whether something's German or not, and this is the whole field called language modeling. They didn't have that back then. Yeah, so they were exploiting a particular thing. By the time the war started, then the Germans had much better machines. And this method no longer worked, so in England they developed a real proto-computer to solve this problem. And can you see anything wrong with this picture? At the end here we get German. This guy doesn't know German. Make it, so we have to have some translation in here. Wouldn't it be great if a machine could translate? All right, so we'll get that. So, okay, so now I'm in position to give the outline for this talk, I think. Okay, so what we're going to do is going to break a series of codes, and we're kind of all the work that was done on building computer software to decipher codes is still classified for the most part. This was done after the war in the National Security Agency and their counterparts, and they still don't give the methods, so we have to kind of reinvent stuff. And I'll come back to that in a minute, or later. So we're going to look at, but our goal is to see if we could treat foreign language as a cipher. But that's such a hard problem, we're going to work up to it by first doing simple letter substitution ciphers, and then we're going to look at phonetic ciphers where sounds are substituted, and have some applications, maybe impractical ones in archaeology and practical ones in transliteration. Then look at word substitution. Instead of letters being substituted, whole words being substituted, and then we'll be in a position to look at foreign language as a cipher. And then if you're patient enough to listen to all that, then I have a bonus, which is a couple of historical ciphers, and then some final thought. So you're here. Okay. So a letter substitution cipher, simple one, is works like this. You have some plain text alphabet. You have a permuted alphabet, which is the cipher. And so if you want cipher alphabet, and so if you want to encode hello world, instead of typing HELLO, you type NMYYT according to the substitutions here. And as an enemy, you intercept the cipher, realizing that in this case, unlike the Enigma, the substitution is fixed, it doesn't move. And you ask yourself, what key, which is this sequence here, if applied to the ciphertext, would yield good plain text. And again, let's start with a human solution to this. So the American Cryptogram Association, which my dad is a member, they make puzzles for each other. Maybe you've seen these in the newspaper. So here's a puzzle. I usually don't solve these by hand. They actually, they don't like computers in this association. So I'm always proposing this algorithm that, no, the whole point is we have fun deciphering these, and the computer's just going to suck all the fun out of it. So we're still wrestling a bit about this. So this is how I did it anyway, as a person, by borrowing kind of their techniques.
The key is clearly an A, right?
It could be an I. Yeah, right. That's a good place to start. All right, so here's what, and we're going to do something similar. So first we do a frequency analysis, and then here's a trick they do, which is a funny trick. They look at the infrequent letters. So here I put a dot over the infrequent letters. And it turns out in English and tons of other languages, the letters surrounding the infrequent letters are vowels. So Q and K, and L and K, and Y and Q. If you keep looking at those tend to be vowels, just the way a language seems to work. And so here we have some vowel candidates. We could say K is A. We could say Q is E. So far, so good, because we didn't create, for example, AE, which would be a tip-off that we had done the wrong thing. But still, we have to be willing to erase. So for example, if we say T is O, that's our other vowel candidate. This doesn't look so good, right? So this is probably not an English word. So maybe one of those three decisions was wrong, so we can back up and say maybe Y stands for O. This looks pretty good. Oh, it was not I. Oh, it was A, just like you said. Okay. How about this? We can start to use our lexical knowledge too. So far we just used our knowledge about which letter pairs are good or bad, but we could use our knowledge about what's a good English word or not an English word. So what do you think about this one?
Cleaning. Cheese.
Sleeves. Is that how you spell sleeves? About freeze. So if you tried those other ones, you'd run into trouble. But if you try freeze, everything still looks good. And then you look at which letters are left over, so on and so on. Keep going. And so it says, auto repairman to customer. If you wait, we can freeze your car until future mechanics discover a way to repair it. So this is the American Cryptogram Association. You get a little reward every time you decipher something. And some people like making the puzzles. Some people like solving the puzzles. There's the leaderboard. You know, it's the exciting. Okay, so now let's look at computer algorithm. So I assume there have. Let's just take one approach. So there's many approaches, and we have many approaches, but I'll just talk about one here. So this is going to be a generative probabilistic modeling solution. So we make up a parameterized model that says, how did this ciphertext get there, the one we observed in the world? And we make up a story that says, first, someone produced a plain text, P, according to some probability model. This could be, for example, just a 26 by 26 table of letter bigram. So given the letter A in English, what's the probability that the letter P is next, as opposed to? So it could be just a simple tiny table. That's all the knowledge of English we assume here. And then someone, same person or a different person, substitutes for every plain text letter token P, some ciphertext, also according to some probabilistic, yeah.
Sorry, dumb question. I don't really understand what those boxes.
Okay, so this one is something like, let's say you see the letter C in English. Should you produce an A or a B or a C or D or Z next after C? And in here it'll say 0.02. So the chance of an X following A is 0.02 versus something else following an A. And this is just, if you see an A in the plain text, how will you encode it in R? And in fact, the true table here might be you encode it as an R 99.9% of the time, but sometimes you encode it as an A because people make mistakes if you're just trying to model this process. So this is a story about how that ciphertext got to be. And you can train these things using a bunch of math. I won't go through all this. Maybe this is the least exciting part for some of you and the most exciting part for others. So all I want to say is that there's some standard methods. Use language modeling techniques from computational linguistics. Use the EM algorithm, which is my favorite algorithm for the learning, unsupervised learning. And use the Viterbi algorithm, who is one of my favorite people because he gave $50 million to USC, and to do the final decoding. Okay, but the goal of all this is somehow to learn this table.
Have you met Viterbi?
No, I attended a talk he gave just recently, though. And I've never seen any of that $50 million either. It's generous, nonetheless. All right, so this is just a method for learning this key and then applying it to it. And if you use this method, you can see that the results are here. So here's the length of the cipher on the x-axis, longer to the right. And here's the error rate, how many letters were deciphered correctly. And you can see the more data the machine is given, the more accurate the translation is. The blue line is if you only, the only thing you know about English is which letters follow which other letters. The red line is just slightly more knowledge, which is given 2 letters in English, like AP. What's the chance the next letter will be, say, L, the trigram model of English. And so those are kind of some initial lessons to learn. Then we looked at the data and found some typical error cases, which involved the language model. This guy, he's voting too heavily. And so if you give this guy some extra weight, then you get a much better result. So instead of half the letters being decoded incorrectly, only 10% of the letters. So this is the same knowledge of English. You can have a better deciphering method, algorithm, that's more accurate. And if you have a 7-gram model of English, this gets down almost perfect on a 100-length cipher. It's interesting to look at, humans can do about a 30-length cipher. And there's some theoretical results from Claude Shannon that explains that, that we also have played around with. I don't think it's here. But, so you should be able to decipher much shorter things. OK, so that's all I wanted to say about letter substitution. So now let's go up to a more complicated type of code, which is phonetic decipherment. So let me see where we are here. OK, so let's say we, you'll have to bear with me for a minute here. You remember how the Spanish invaded North America, like the Mayan people, and they discovered all these Mayan tablets, ancient tablets. OK, and then the cities got overgrown, right? And then eventually, in the 1960s, they were able to decipher those Mayan tablets. And they couldn't use the modern-day Mayan Indians because those people couldn't read or write anymore. They couldn't read their ancient script anymore, so they had to decipher. OK, so I'm not going to work with the Mayan script here. I'm going to instead ask you to believe that the Mayans invaded Spain 500 years ago, killed everybody who could read and write. And eventually there's still some Spanish people who talk Spanish, and the Mayan scientists dig this out of the ground, and they want to be able to decipher it. OK, sounds OK? OK, so the Mayan scientists ask themselves, how did this get here? And this Mayan guy named Warren Weaver says, when I look at these squiggles, I say to myself, this is really a sequence of Spanish phonemes, but it has been encoded in some strange symbols. Let me decode. So here's his theory. Someone first produces a sequence of Spanish sounds, and then someone encodes those with these squiggles. And so you're basically trying to figure out what's the relation between those sounds and these letters. And that's something that nobody knows and is left for unsupervised analysis. And to do that, we can again use the same methods and get 93% accurate phonetic decipherment. So we can take this, play it out loud, and a modern Spanish person can listen to that and understand it. So it's a kind of application of this kind of decipherment to archaeological. And I'll return a little bit to the end here, but it's still pretty open how computers can contribute to this kind of archaeological decipherment. OK, let's talk about this. So here in setting up this model, we assumed that this is the Spanish, represents Spanish spoken language. But what if you dug this out of the ground and you had no idea what the spoken language was behind it? That's more unsupervised. Is it OK? I don't know what language this is. OK, so one thing you might do is build a universal model of human sound production. And it doesn't know about any particular language, but it knows that a sequence like k-a-n-a-ri is OK. People will say that. Wherever they live, that might be a reasonable thing. But they probably won't say er-tik-erk. So we want a general model. Yeah, check. OK, and so what we want to do is find a substitution table that sounds out the text in a way that is sort of reasonable for a human, sounds human, as opposed to sounding Spanish. And linguists actually know a lot about how to make these kind of sequences look better than these independent of language. So one interesting thing is the syllable sonority structure. So it turns out words are divided into syllables, and those syllables, each syllable goes like this, more or less. There's a quiet consonant, like a loud consonant, like then a vowel, which is very loud, and then another loud consonant, and then a quiet consonant. You may not have all 5 of those. That's the kind of structure. And syllable after syllable kind of tends to work that way. And that's why something like dram sounds good to a human, but erdam doesn't sound as good because the D is quieter than the R. And there's a bunch of other stuff here. So now let's look at the same text and come up with a different theory of how it got there. We're not going to make it Spanish specific now. So we say, oh, someone, to write down each word, first someone decided how many syllables mentally. They decided the type of each syllable, whether it's a consonant vowel or consonant vowel consonant. They decided to maybe make diphthongs next. And then finally they decided for every V or C that they've produced so far, actually write down, pick a letter. So for V, you might pick A with high probability and R with low probability. And so that's a kind of theory about how this text got produced. Maybe it's not a great theory, but it's maybe good enough to uncover some properties of this. And all this is unknown, and we use EM algorithm. So if I put a 0.04 in there, does it increase or decrease the probability of seeing this? If I take that 0.04 and raise it to 0.06, does that make this look more plausible or less plausible? And so EM figures all that out. And as a result, you can see the kind of unsupervised learning. All it's given is the text that you dug up out of the ground. And what it concludes is, for example, this 6-letter word is 3 syllables. The first 3 letters are the first syllable. And in fact, it's consonant, consonant, vowel, or loud consonant, soft consonant, vowel. That's how it interprets the PRI. And there's 2 other syllables. And it says this word has 1, 2, 3, 4, 5 syllables, and so on. So it's uncovered a lot of the phonetic structure of the language. But it, oh, thank goodness. I was like, some people are looking up, and you're looking at those screens, okay. Because this is the board face, right? All right, so, where was I?
At the bottom of the slide.
Yeah, bottom of the slide, no doubt. Okay, that's why, okay. All right, so one thing you can see we didn't quite get to the answer is, how is this I pronounced? What's the actual sound? Is it A or E or or O? And so what we don't know is, we know that it's a vowel of some sort, but it's future work to kind of figure out what how that letter's actually sounded out. And I think it's possible, but it remains for the future. Okay, so next we go up to a more practical application of sound substitution ciphers. So if you go to Japan, you see a lot of signs like this everywhere. And if you know the sound values for these things, this is ko, hi, ko, na, coffee corner. And so Japanese borrows a lot of words from English, and they use a special alphabet, syllabary, kind of for this. Ka, aga, te, I don't know this one. I know this one. Tosto. So for 420 yen, you can buy toast at the coffee corner. And so Warren Weaver says, when I look at these signs in Tokyo, they're really written in English, but they have been encoded in some strange symbol. I will now proceed to decode. So he's actually right. This is the first time where Warren Weaver's right on the money. These are English, and they've been encoded. So if you're given a dictionary of, how do we figure out the various sound values here? And it's actually complicated mapping. So Japanese has 5 vowels, English has 13 vowel sounds. There's no F and H distinction in Japanese. And it's a complicated mapping. And we found we could learn this given a parallel data. So a bunch of Japanese words with their English expressions, we can align them. But then later we tried, with some success, to do it in a non-parallel way. So we don't actually need a dictionary. So here's the setup. Imagine yourself, you're in Tokyo, you see all these signs all the time. You got a notebook, you keep working. And what you're trying to do is come up with sound values for this that makes everything seem like English. Now, if I apply these sound values, it doesn't look like English. Keep going. And then one day you go, got it. Everything's English for you. And that's the kind of unsupervised, super unsupervised realm that we cover here. It's not quite as good as this, but it's progress, yeah.
If you go back one slide, when you got to the stage where you have ingenioso as this set of symbols, you could at least make a conjecture that this corresponds to some modern language. Right? And if you do, then you can go look for modern languages that actually have this set of patterns in them and perhaps guess which one it might be.
That's right. an alternative, even another alternative, going back 2 more slides, is just to take this guy and just try French, try German, try French. Yeah, that's even now. More brute force, broody force way to do it. Okay, so now we're done with this part, and we're going to go to this part. So word substitution is kind of a funny problem. It's not really a... Oh, this is a very practical thing. So as soon as we started translating Japanese to English, we found out all the OOVs, out of vocabulary words in Japanese, they're really English words encoded in these strange symbols. And so you have, for all those, if you want to translate them, you have to kind of sound them out. So this is a practical thing. Okay, so here, word substitution, there are some codes, military codes that do this. So it's like, you know, I'll deliver the lingerie to you in, you know, Mexico. Meaning I'll, you know, deliver the rifles to you tomorrow or something, right? And so they agree beforehand to substitute words instead of letters. Or imagine I go to your hard drive in the middle of the night. You're at home. Every document you have, every time the word "the" appears, I substitute the integer 10542. And every time the word device appears, I substitute integer 457292. Now, you get back to work in the morning, your hard drive is full of just these integer sequences where previously you had English. So can you recover the English?
I just recently had binary.
Huh? Yeah, okay, not that hard. Not that hard. Right, I don't want to mess with your binary files are still okay. Just replace your English files. And so obviously now we're in a realm of a more difficult cipher to solve. But that's where we're working now, because foreign language translation is much more like that, where we don't just, you know, really translate whole sentences and text. Is much more like that. So let me just skip word substitution, although it's an interesting problem, and just go straight to this. So Warren Weaver says, when I look at this giant corpus of Arabic, let's say billions of words, I say to myself, this is really English, but it has been encoded in some strange symbols. Let's decode. Okay, so at first it seems like a crazy idea. You just look at all this Arabic and somehow you're going to figure out what it means in English without any Rosetta Stone. Okay, but on the other hand, we have this method, and we can just use that method. So we make up some story about how people produce English word sequences. And if you know about speech recognition or other, we have those models. They're already done. And we can make up another kind of model about how English becomes a foreign language. So maybe words get substituted and reordered, something like that. So we can do that too. And so this kind of problem we brought up, you know, 10 years ago. But at that time, there was no practical way. So just the table here, if you wanted to run the EM algorithm, this table is something like 100,000 word types this way and 100,000 word types this way. That's a big table. It doesn't fit in memory, much less the actual processing to determine these values. So that kind of problem kind of sat there for a while, awaiting better techniques and not better techniques. Okay. So before I get to those techniques, I guess just like we've been doing, since it seems like a crazy, impossible thing, let's just do it by hand first and work out how a human would do this, and then we'll turn over to the machine. So here's how a human might do this. So we've got, in fact, I did this over Christmas break many years ago. I took this time expression corpus of foreign time expressions, which someone made for me, 500,000 of these, pulled out of a foreign newspaper. And I said, okay, I want to try to decipher these into English by hand. So already you can see those two words there might be month names. So if you pull out everything that appears in that kind of pattern, you get, unfortunately, not 12 month names, but about 24 month names. So that's okay. Seems like progress. And let's pick this one. That's one of the month names that we get. And we can see, give me every context that it appears in. Okay, and we can look at the top one. This occurred 13 times. And anybody have any idea what month? Now we're narrowing down which month that actually is. So if you know a lot about history, you might be able to figure this out. Or you can just go to a search engine and type in all these, and you'll find out that this one is much more frequent than the other ones. And in fact, this is the Six-Day War between Israel and Arab countries. So the point is, we can take this word and we figured out that it means June, using, by hook or by crook. We did it, so that's good. And now we can find out what other words this thing appears with. These seem to be the most common phrases that it appears in. So anybody can guess what this word means or this one? So a good way to think about it is now we go to an English newspaper and we look up the word June. What occurs with June in English newspaper? If you do that, it's something like last June, next June, things like that. And so this is the part of the Christmas holidays where I go, okay, that's enough. I can't do this anymore. But probably one of these means next and one of them means last. And you can see we could keep going from there. But since computers are good at number crunching, and finally the techniques catch up, we can do this. And so, for example, this is just something we're writing up right now. We take English text and foreign text, we put it through a deciphering engine, and get out a bilingual word-for-word dictionary. That's our goal. On the x-axis here this is Spanish. How many Spanish tokens we have? 100 million, up to 100 million words of Spanish, with no parallel English. And then on the y-axis is the quality of the bilingual dictionary that we're able to pull out through this deciphering. And if this is one method you can do, I don't have time to go into a lot of details. It's kind of a bigram, adjacent bigram. And if you use some syntax, actually, of English and Spanish, you can do better. So you can see gradually we do better and better given more and more Spanish text. So here it's not like deciphering a 30-letter message. To really learn these bilingual dictionaries, we need tons and tons of text for a language. But luckily, there is tons and tons of text for a huge number of languages. So we hope that we can keep doing this, get better and better, and bring in better techniques to not only keep this line going up, but also to build better graphs here. So that's how we could build a dictionary. And we also started trying to build a whole translation system. Yeah?
Sorry, that Y scale, is that F-score?
This is for every entry is that Spanish-English word pair found in a Spanish-English dictionary that was computed from a parallel corpus.
So those are percentages?
It's accuracy. It's the, yeah, it's a percentage. Thank you. So